In this lesson, we'll continue our discussion of the chemical level of organization by looking at the different types of chemical reactions that occur in our body. We'll then take a look at enzymes, which are necessary to speed up these chemical reactions or even to get these reactions to happen. And then we'll finish by taking a look at some definitions of some inorganic and organic compounds that are important to anatomy and physiology. So let's begin by looking at chemical reactions. In a chemical reaction, either two things are happening. Either new bonds are being formed, like we're making something, or existing bonds are being broken down. Just think about like digestion, maybe, right, where we're going to break down foods. So chemical reactions, either new bonds are formed or existing bonds are going to be broken. Now, we know from a previous lesson that the reactants are the materials that are going into a chemical reaction. And we said by convention, we typically write them on the left-hand side. Right? It's not always the case, but we typically write them on the left-hand side. Then there will be an arrow, and then the products are the materials that come out of the chemical reaction. Those by convention are written on the right hand side. Okay, so the reactants are the things going into the chemical reaction, and the products are going to come out of the chemical reaction. It's what we're making. Another definition that we did earlier on in one of our first lessons is metabolism. This is related to chemical reactions. Remember that metabolism is the sum of all chemical reactions that are occurring at one time, whether we're making something, right, new bonds are being formed, or the existing bonds are being broken, right? They're all part of our metabolism. Okay, a couple of definitions related to chemical reactions that we need to cover first. The first one is work. Right? By definition, work is the movement of an object or a change in matter. So just us moving around throughout the day, right? We walk, we run maybe, we exercise, just our normal activities, body movements, that is actually considered work. But on a more of an inside level, even just the synthesis of biomolecules, if we make proteins, if we make triglycerides, right? That actually is work also, right? Where you don't really see that kind of movement, but those things are happening inside of our cell. Even the conversion of liquid water, right, which is a form of matter, to water vapor, right, where we change it into a gas, that would be considered work. We're changing matter. Okay, so all of these are work. But in order to do these work, we need energy. So energy is the capacity to do the work, right? Without energy, you wouldn't be able to move. Without energy, we wouldn't be able to produce different chemicals that we need inside the body, right? So this is what we're going to talk about now. Energy is the capacity to do work. Now, there's two types of energy that are important to anatomy and physiology. One is known as kinetic energy. When we're using energy to do work, right, we're actively using that energy is being released. We call that kinetic energy. This is the energy of motion. But other times we have energy, but we're not using it. We're actually storing it. We're saving it. This is known as potential energy, right? And a great example here would be like a battery, right? Say the battery in your car or a battery in your phone or some appliance. When you're not using that appliance or your car, the battery has energy. It's just sitting there, right? And let's say that your car is waiting for you to go in and start it. But while the battery is sitting in your car, it's not using the energy to put on your lights. It's not using the energy to do your windshield wipers. It's not using energy to run your radio. It's just sitting there. That is stored energy because once you go into your car and you put the key in, the battery will be activated to start your car, and then we could do all the things we do with our car. In the body, we can actually store energy in chemical bonds. We actually call this chemical energy, right? So this is a form of potential energy, right? It's stored energy. It's energy again that has the potential to do work. One of the places that we store energy in our chemical bonds is known as ATP. This is a little bit advanced. You don't really have to worry about this too much right now. I just want to introduce it. ATP is a chemical known as adenosine triphosphate. That last bond, the last phosphate bond, is a high energy bond that is stored energy. Once we break that bond, that energy is released and we use it to do energy. Okay, so energy, again, is the capacity to do work. We can't do work without energy. The two types of energy we want to know are kinetic. This is the energy of motion. This is the energy that we're using to do work. Potential energy, think again as a stored form of energy like a battery, right, in outside the body. That is stored energy. Once we turn that battery on, it releases the energy. In the body, we have, like batteries, we have stored energy in the form of chemical energy. Some of the places we store this energy are in chemical bonds. And again, the big example we're going to look at this semester is ATP, right? Again, that last phosphate bond has a lot of energy stored in it, but we'll do that more when we get to biomolecules. Okay, let's take a look at the different types of chemical reactions. There are four of them that we're going to study. Decomposition, you can kind of guess what that is already if you know just when something decomposes. We'll take a look at synthesis. That's actually the opposite of decomposition. We'll take a look at exchange, and then we'll finish up with reversible. So decomposition, we also can call catabolism. Right? Sometimes they say catabolic, right, or catabolism. These are chemical reactions that breaks a molecule into smaller fragments. Right? If you think about like digestion, right, just kind of from what you know, we're taking foods that we eat and we're breaking them down and we're going to hopefully get energy from them. So decomposition, here it is right here, breaks chemical bonds. That's what's important. It's going to break down chemical bonds. And like I said, we commonly see them in the digestive system. So here's a simple way of indicating or notating, remember chemical notation, a chemical reaction that is decomposition. If we start with a reactant, let's say AB, yeah, whatever this may be. Here's our arrow. And then when we break AB down, we end up getting now two different products, A plus B. That is a classic way of writing decomposition reactions. Now, sometimes we actually do decomposition by adding this guy right over here, H2O, which is water. We actually need water to break down uh, the reactant going in. When we use water, this is an important word, we call this hydrolysis reaction. Hydro means water. Lysis means to break down. If I said to you, a patient has osteolysis. Osteo, you probably know, means bone, and then lysis means to break down, right? So their bones are breaking down for whatever reason. So that's in medicine we use lysis, or healthcare we use lysis a lot. It's an important word. So notice what we did here. We took the water to break down the AB, right? So here one hydrogen goes with A plus the B gets the other OH, right? H2O. Okay, so we'll see this when we break down carbohydrates, triglycerides, proteins. These are all going to be hydrolysis reactions. The second reaction, if you just want to jot down, I said it before, but if you didn't write it down, this is synthesis reaction. This is the opposite of decomposition. Now we can also call synthesis reactions anabolism, right? Or anabolic, they sometimes say. Right? So synthesis reactions or anabolism. These assemble smaller molecules into larger molecules. So if we're going to make, let's just say, a simple sugar, again, you don't have to write this example down, these are a little bit advanced, but let's just say we took a simple sugar that you may know, glucose, and we add it to another simple sugar that you may know, fructose, right? Fruit sugar. So if I take a glucose, let's just say for instance a glucose would be A and B would be fructose, and I put it together, I get a sugar called sucrose. You know what that is? That's table sugar, right? The typical table sugar that we use at home. So that would be an example of a synthesis reaction. All right, so here we're going to actually form chemical bonds. If I go back a minute, what did decomposition do? Break chemical bonds. So you can see these are opposite. Okay, so how can we write this? Our chemical notation would be the reactants, again on the left, A plus B yields a new product, which we write on the right, AB. Now, we said before, I'm going to go back a moment, hydrolysis reactions are reactions we use for decomposition where we add water. Watch this. With synthesis reactions, we sometimes have a synthesis reaction, believe it or not, where we have to take out water to form the bonds. This type of reaction is known as a dehydration synthesis. We're going to remove water to form a bond. We sometimes call them condensation reactions. I typically say dehydration myself, but you do see this written condensation. It's the same thing. So let's just say we have a reactant A, we have a reactant B, right? But this A has a hydrogen on it, this B has an OH on it. So watch this, guys. We could take out H2O. We remove that molecule of water. Here it is. And now we formed a new substance over here. Like I said, we're going to see this when we do the synthesis of biomolecules, carbs, triglycerides, which are fats, proteins. All of these, when we make those substances in the body, we do dehydration synthesis. Okay, we're just removing a molecule of water. And think about it, when you're dehydrated, what are you lacking? Water, right? So it's an easy way to remember it. Okay, so that's a synthesis reaction. The third chemical reaction is known as an exchange reaction. We're not going to do this too much this semester. It's a little bit advanced. In A&P2, usually when we study buffer systems, we will talk about exchange chemical reactions. So we'll just kind of define it this semester. But this is a chemical reaction that involves decomposition first. So we have to break things down, and then we actually reorganize things and then do a synthesis reaction. So watch this. Like I said, these are commonly seen in buffer reactions. Buffer reactions are reactions that help to control too much acids forming in the body. We don't want to become too acidic, so we have buffers that actually prevent us from becoming too acidic or too alkaline. Again, it's a little bit advanced at this stage. So watch this. Let's just say we have a reactant over here, AB. We have another reactant over here, CD. So the first thing we need to do is to break these down. That would be decomposition. Then we reorganize these where A goes with D and B goes with C, right? So now we have new products, AD plus CB, right? We did synthesis, but we didn't make the same thing, obviously. We reorganized them to make new things. And when we get to acid base, I'll give you an example of a buffer reaction. Again, it's a little bit advanced for A and P1, but I'll demonstrate it. I just want to wait. It's a little bit too early at this point here. All right, so this is what we call an exchange reaction. What you should know right now is that it involves decomposition first, then synthesis. The last type of chemical reaction we want to look at is known as a reversible reaction. So the first thing you should note when you look at this, you see the products, I'm sorry, the reactants on the left, right? Reactants are on the left. The products are on the right. But notice the arrow this time looks different. If I go back a moment, the arrow here was one way, right? Synthesis arrow is one way. decomposition, arrow is one way. With reversible reactions, that means this reaction can run this way. As the amount of product builds up, say we have too much of this now in a cell, the reaction can go back the other way. Right? As these reactants build up, the reaction can go this way. So we can go both ways. So they call it reversible. So that's why they draw the arrow um, with the two sides, right? So at equilibrium, the amounts of chemicals do not change, even though reactions are still occurring, right? So the reactions could be going this way or this way. They're going back and forth. Reversible reactions, they seek equilibrium. And this is a word, again, we did this in our very first lesson. Equilibrium is a state of balance, okay? When the reactants are added, right? So let's just say we add more reactants or more of these come into the cell, the reaction rates will be adjusted to move this way. But if too much AB builds up, right, we can't say let's go into another chemical reaction. Too much of this builds up. Guess what it does? It goes back the other way, right? So the reaction rates, they adjust to form that equilibrium or reestablish that equilibrium. Okay, so that's what we call a reversible reaction. Now, biochemical. Well, actually, those are the four types. Let's take a look at enzymes now. These are important to chemical reactions. And you may think about maybe a time where you were in high school and you were maybe in a chemistry class and you had your goggles on and your lab coat and you were going to do some type of experiment where you're going to make something. So you had this little spoon and you put some chemicals in it and you remember holding it over that flame. They used to call it a Bunsen burner, and you would put that over the flame, and the heat of the flame would actually cause the chemical reaction. If you didn't use heat, the chemical reaction wouldn't probably occur. So you may know we need to put energy in to chemical reactions to get them to happen. So in cells, that is true. Chemical reactions do not occur spontaneously. And if they did, they would happen very, very slowly, right? We need to have enough energy to activate those reactants. We need to put in energy to get that reaction to happen. It just doesn't happen by itself. So there's a term we use, activation energy. This is the amount of energy needed to start a reaction, a chemical reaction. Now, like I said, in our body, we don't have little Bunsen burners, right? These little flames to get chemical reactions going. There's really not a lot of energy. So what we have to do in order to get the chemical reaction to take place is we have to lower this energy requirement that we got to put in. We have to lower the activation energy. And guess what? We have chemicals in the body known as enzymes. They do that for us. Enzymes lower the activation energy. So now the chemical reactions will happen much, much faster than if we didn't have the enzyme. Okay, so enzymes will speed up the chemical reaction. We'll see later in the semester, they go into the chemical reaction and then they come out. They're not part of the product, right? They don't become part of the product. But we'll talk about that in a future lesson. Okay, so again, in chemical reactions, in our cells, these chemical reactions do not occur spontaneously. There's not enough energy, right? We have to put in energy to activate those reactants. What do we call that energy? Activation energy, right? That's the amount of energy needed to begin, right, to start that chemical reaction. So we can't add more energy to get the chemical reactions to happen, but we can lower the energy requirement. Who's going to do that for us? Enzymes. Let me show you what I mean. Here's a great diagram or graph showing this. So just kind of watch over here. Over here we're showing the reactants. Right, so let's say A plus B. Now, normally if we wanted these reactants to form a product, we would have to put in, follow this dotted line here, we would have to put in that much energy to make our product. That's a lot of energy, right? Our cells don't have that amount of energy. So watch what happens. If we add an enzyme to the chemical reaction, and here they're showing you, look at the curve now, guys. The amount of energy we need is substantially lower to form that product. All right, so without the enzyme, we wouldn't be able to put enough energy in to get the chemical reaction to take place. Okay. Now, our chemical reactions sometimes release energy, but other times we have to actually put more energy in than is released from the chemical reaction. Let's take a look. The first definition I want to go over is known as exergonic. Think of exer as exo. So it's going to release, like exiting, right? It's going to release. This is a form of chemical reaction that releases energy. A lot of times that energy is in the form of heat, and we use that heat to help maintain your body temperature, right? Your 98.6, right? That's coming from the heat that's released from our chemical reactions. So here in this case, guys, the amount of energy released from the chemical reaction is more, right? Greater than the activation energy, the energy that we had to put in, right? So we did have to put energy in to get the chemical reaction to take place, but the chemical reaction itself gave off more heat than we needed, and that's known as exergonic. Just the opposite. Endergonic reactions, ender, think of endo, right, kind of going in, absorbs energy. Here, the amount of energy required to begin the reaction is more than what is released. We typically see synthesis reactions are endergonic. Right, and think about it. If you're going to build something, let's say you're going to build a house, it just doesn't build itself. You have to put in energy to build that house, right? Manpower, horsepower that they say. We have to put all that energy into building. Well, it's the same thing in our cells, right? We have to put in energy to build different things like proteins. Okay, so exergonic releases energy, endergonic reactions absorb energy. And finally, the last slide for this lesson. Let's take a look at some just different types of inorganic and organic compounds, just some basic definitions. So we'll take a look at nutrients, right? Most of you know this already. These are essential molecules that are obtained from food, right? So all the nice healthy foods that we eat, we need these nutrients for, here we go, physiological function, right? Physiological means functioning, right? For our cells to function. Now, sometimes we make chemicals in our body as part of chemical reactions that we don't get from the diet. These we call metabolites. If you go on in biochemistry and you kind of study different pathways of chemical reactions, all these things that we make or break down are referred to as metabolites, right? They're not in from the diet. They're from different chemical reactions in the body. So these are either made or broken down in the body. There's two basic categories of nutrients and metabolism. We have inorganic compounds and organic compounds. So things that are inorganic are not based on carbon and hydrogen predominantly. Even though carbon dioxide does have one carbon, it's not like a big molecule where it's mostly carbon and hydrogen. So CO2 is considered an inorganic compound. O2, inorganic. Water, right? H2O is an inorganic compound. Inorganic acids, what's a good example you know? Stomach acid is called hydrochloric acid, HCl, right? Bases and salts. Bases would be like potassium hydroxide, KOH. What's table salt? NaCl. All right, so if you notice, these are not based solely on carbon and hydrogen. Organic compounds, these are molecules that are based on the presence predominantly of carbon and hydrogen. So we're going to see when we do organic chemistry, carbohydrates, proteins, lipids, which are fats, nucleic acids, which are DNA and RNA. These are huge molecules, huge with, just an abundance of carbon and hydrogen. So these are classified as organic compounds. Okay, so that concludes this lesson on the different types of chemical reactions, the function of enzymes, right, to lower that energy requirement, and then just an overview of various types of organic and inorganic compounds.